Hi everybody, welcome to week 5. I am slowly recovering from my sinusitis cold flu thing I have. So please do excuse any coughing or anything of that nature. I cut last week's session short because I thought trying to run those two topics back to back might be a bit much. And the first topic is the knowledge there is required for the second one. So I thought a little bit of time to sort of sit on that and stop, not stew, but to process the information, and then we can use it again here. So this leads on from the Lewis structures that we were building last week. The bonding pairs of electrons is what makes the molecular shape, the 3D shape. So if you look at the ball and stick models, they are pretty good at predicting. We can sort of, based on where the electrons that bond are, we have this VSEPR theory, which tells us that electrons will arrange themselves in a manner that reduces the repulsion because they're both negatively charged. So the further away they are from each other, the better. And the shape of the molecule depends on how many of these electrons there are. And we'll look at the mole. I'm not sure if it's next week or the week after. I'm pretty sure we'll put it next week. We'll look at stoichiometry. And this is really important to know before we get into anything with stoichiometry. So, molecular geometry and the mole. It's a little bit dry. I mean, most of your 11 or 12 chemistry is pretty dry. So, as I said before, I slightly adjusted the schedule. I'll either do it, if I don't manage to catch up, I will either do an extra video during the week or I'll do an extra week at the end. So, I've done a lot of this stuff before, not really in this format. So this is a mishmash of some different presentations that I've given over the years. So really so have the other ones. So molecular geometry, and it's a fancy name for what shape will a molecule be, and we can accurately and precisely predict the shape based on the Lewis structures that we were building. So depends on the number of pairs of electrons that surround the central atom, and there's lots of different overly complicated formulas that they like to teach you. I'm going to teach it the simple way, as that's, I think, the best way. And there's rules that govern where the electrons will be found, depending on the number of pairs, and where those electrons are found. Sorry if that looks weird, I just restarted the recording, so I have to top information. So the number of electron pairs will govern where those electrons will be found, which will govern the shape of the molecule. So this valence shell electron pair repulsion theory, or VSEPR, is used in chemistry to predict the geometry of individual molecules from the number of electron pairs surrounding the central atom. We built the models last week doing the Lewis dot structures. And now we'll look at how we can predict the shape. And this, again, I'll teach you my simple way. Why are we loading? Sorry everyone, it wasn't letting me share the full screen of the video, of the presentation once the presentation was started. So the first is the linear molecule. The simplest, the electrons arrange themselves in a straight line, or a 180-degree angle. It's the simplest form of molecule. Not the simplest form of molecule, but the easiest one to predict. That you've all got your notes with you because I'll pretty much be using the whiteboard. So, again, I just did this. Students. So, linear molecule ranged in a straight line. There are two electron pairs surrounding the central molecule. Well, the central atom, it's not the central molecule, sorry, the central atom. The writing hasn't gotten any better in the school holidays, that's for sure. So, we go to the next slide. Beryllium chloride. So they say, what is the molecular geometry? I'm going to take this way back. It's everything we've learned so far. So I'm going to take this all the way back to what we learned and why, and hopefully show you why it's important not to miss a step in chemistry. So beryllium chloride. Beryllium. So what we need to do is figure out the formula for beryllium chloride. Beryllium is in group 2. Chlorine is in group 7. So we have beryllium contributes 2 valence electrons because it's in group 2, and it forms a 2+ cation because it's in group 2. Chlorine is chlorine minus. So beryllium chloride, its formula would be because we need to have a 2- charge here to match the 2+ charge here. I need a new set of pens. So beryllium chloride is BeCl2. Beryllium is in group 2, it will form 2+ cation. Chlorine is in group 7, it will form a 1-. Need to balance that charge with BeCl2. So if we remember, the most electronegative atom, sorry, the least electronegative atom goes in the middle. Beryllium being on the far left sits in the middle with a chlorine atom either side. So we go back to our Lewis dot structures. So we know that beryllium contributes 2 electrons to the bond because it's in group 2 and there's 2 chlorines, so they both contribute 2 electrons. So there's 4 electrons altogether. We know there will be 2 pairs. So beryllium chloride will be a linear molecule. We go next, we go to, or the bonds are at 180 degrees from each other because they're physically trying to be as far apart as possible. So 2 pairs is linear. We go up to 3 pairs. This creates what's called a trigonal planar molecule. So, sorry about that. Trigonal planar, or 3 pairs, looks like the shape you can see on slide 9. It means that around the central atom there are 3 pairs of electrons, so it's obviously not going to be a straight line. And this is where we start getting into the weird shapes. So BF3, the boron trifluoride, and this will bring us to another exception to the rule. So boron, BF3, is in group 3. It has 3 valence electrons, so it contributes 3. Fluorine is in group 7, so 1 times 3. Because there's 3 of them, 3 fluorine in group 7, it contributes 1 electron. So we've got 6 electrons in total, so 3 pairs of bonding electrons. So we build the Lewis dot structure, we have, and this is different, the boron trifluoride. So there will be 3 sets of bonding electrons. And a lot of the time they won't actually ask you to draw it, they will just ask what the shape will be. Boron is in group, so the way to calculate that in an easy way, boron group 3, so it will contribute 3 valence electrons. So by this, you know it will form 3 bonds. Can't form any more than that. So you know that if it's got boron, it's trigonal planar. So there's another one. Tetrahedron. I'm not going to try and draw one because I'm not very good at drawing. And an example of a tetrahedron is there are 4 bonds, 4 bonding pairs, or 4 bonds. So this would be tetrahedral. I need a new whiteboard desperately. So 4 bonding pairs is tetrahedron. Again, let's look at it. An example that fits the mold. CH4, carbon is in group 4. It has 4 valence electrons, so it will have 4 bonding pairs. So anything has carbon and hydrogen, it has carbon in the middle, and then you have 4 hydrogen atoms bound to it. My whiteboard markers are dying. So, if it has anything from group 4, it's a tetrahedral molecule. Because if it has 4 valence electrons, then it bonds to 4 other elements. So, you would have carbon in the middle and hydrogen all the way around. And these bond angles, again, are arranged so they're as far apart as possible, and they're 109.5 degrees is the bond angle. So we go on to the next one. Trigonal bipyramid. Once again, I'm not going to try and draw it. I don't hate myself that much to try and draw that. So, example of this is PF5. Guess what? All my pens are dead. So PF5, phosphorus is in group 5. Guess what? Anything with phosphorus has 5 bonding pairs. Because there's 5 valence electrons, there would be 5 bonds. So you have phosphorus and then you have 5 fluorine. It's in the formula there for you. So 5 bonding pairs, it's in group 5, so it will create 5 bonds. So this is what we call the trigonal bipyramid. I'm not even going to try and draw it. The actual image of the shape, I think, is largely irrelevant here. Just knowing what it is. So I might try and draw the PF5. So it would have phosphorus in the middle. Phosphorus has 5 valence electrons, and there's 5 fluorine molecules. Sorry, fluorine atoms. So it would be something like this, with the bonds as far apart as possible. So these bonds, we know that it's in group 5. So phosphorus will contribute 5 valence electrons. There's 5 fluorine molecules. So we have 10 electrons, which gives us 5 bonding pairs, which would give us the shape of the trigonal bipyramid. So these are 90-degree angles here, and then up here we have 120-degree angles away from the others. So this minimizes the repulsion between the electron pairs. So there's one more. I'm going to do videos on all of these, probably like 2 or 3 minutes each, and I'll go through really in detail the VSEPR model of certain molecules in these different shapes. Well, I thought I would just go over it quickly here and go into more detail in the... So the last one is octahedral. Again, I'm not going to try and draw that. That's very silly. SF6 SF6 is, why have I made that full screen? Sulfur is in group 6, so it has 6 valence electrons available for bonding. So we know there's 6 valence electrons available for bonding in sulfur because it's in group 6. And then we have 1 available for fluorine. So we would have a total of 12, or 12 electrons, 6 pairs. So it's really quite a simple thing to calculate, and really you need to know the group of the first atom, and that really should tell you everything that you need to know. So the shape of that would be something like yeah, switch on our windows. Interesting neighbors out there. So that's what SF6 would look like. So an octahedral molecule. And I'm going to go through each of those in a video where I just go from go to woe with exactly how I would figure it out. So I'm now going to move on to, pardon me, the mole. So part 2, the mole. You can't see that because I'm not sharing it. So this is building up to stoichiometry and sort of chopping and changing between units and numbers. And it's something that a lot of people struggle with. So I hope that I can make it a little bit simple for you. So a mole is a name for a specific number of things. So a dozen eggs is 12 eggs. A mole of eggs, I mean, I think I have to type it, 6.022 times 10 to the power of 23 eggs. It is an unimaginably large number. 6.022 times 10 to the power of 23 is 6.022 followed by 20 more numbers, maybe 19. If you had 1 mole of eggs, it would be 3 times the size of planet Earth. And if you can think of the smallest thing that you could possibly see, then atoms are millions of times smaller than that. So we calculate the number of them, not based on what we can see and what we can count, but based on the this number here, Avogadro's number 1, Avogadro's constant. So it's the amount of substance that contains this number of particles. So 1 mole of carbon is 6.02 supposed to be 2, times 10 to the power of 23 carbon atoms. So 1 mole of carbon atoms fits into a jar. 1 mole of eggs is 3 times the size of the Earth. So that is how small atoms are. And that's why we don't use kilograms and grams. So we have the sodium here, sodium metal. And 1 mole of sodium equals 6.023 times 10 to the power of 23 atoms. So I don't even know what 23 to the power of 23, what that is in words. But it's unimaginably large. So 6.023 times 10 to the power of 23 sodium atoms equals 1 mole of sodium atoms. So when we look at, if we look at, we can calculate the amount of something based on the moles. And if you look at the periodic table, you'll see an atomic mass unit. And that is, on average, how many grams of that substance make up 1 mole of that substance. AMU on the periodic table, it tells you that. So 1 mole of oxygen, again, it's just 6.023 times 10 to the power of 23 oxygen molecules. And this number came from a guy called Avogadro. I used to call him Avogadro, like avocado, for years until someone corrected me. I don't know why. I thought it was Avogadro's number. But yeah, so it was named after this guy, and he's not the prettiest man I've ever seen. So 1 mole of carbon atoms equals 6.023 times 10 to the power of 23 carbon atoms. We can't count it. We can't guesstimate. We can't look at it. We can't hope for the best. But what we can do is weigh it. So how do I know I have 1 mole of carbon atoms? And I hope you've got a periodic table there. And I'll give you 30 seconds to a minute to find the atomic mass unit of carbon. And it will be expressed in grams per mole. So I'll give you 30 seconds to find that. You can Google it if you want. Up to you. Okay, so now we know the grams per mole tells us how many grams, or the AMU on the periodic table tells us how many grams of carbon make up 1 mole of carbon. And you'll notice as the atoms get bigger, obviously that figure goes up. So 1 mole of carbon atoms equals 12 grams of carbon. And you'll be looking at the periodic saying that says 12.01 or 12.011. That's fine. I keep it simple. It's just 12. It's just easier. So I've weighed out my carbon. I have 12. I don't know, 4 grams. I can't remember what number I used. So the 1 mole of, so saying we've got 12 grams. If I have 12 grams of carbon, and the AMU, atomic mass unit of carbon, is 12, then I have 1 mole of carbon atoms. So we weigh it. It never works out exactly that way, and I'll teach you how to calculate between the varying numbers and calculations. Sorry. So 1 mole of carbon atoms equals 12 grams of carbon. 1 mole of sodium atoms equals 23 grams of sodium. So 1 mole of oxygen molecules. Oxygen exists as O2. So we take the mass of oxygen and we times it by 2. So 32 grams. So 1 mole of an element, or the A subscript R, 1 mole of a compound, or M subscript R. So for elements consisting of atoms, it's the mass in grams over the molar mass in grams per mole. Again, I'll put out a couple of videos. This was writing down cam videos here. Again, I'll put in more detail in the videos. So, a substance consisting of molecules, we won't worry about, we'll just look at this one. So, calculate the mass of 1 mole of carbon atoms. So, to calculate the moles, we divide the mass in grams. So we take the number of moles times the molar mass, that gives us 12 grams of carbon. So if someone said we had 50 moles of carbon, we would write 50 times 12, that gives us 60 grams. So again, if we look at sodium atoms instead, we times, if we're saying calculate the mass of 1 mole of sodium atoms, it's 1 times 23. Because we have 1 mole of the substance times 23 grams per mole. So for each mole of sodium contains 23 grams. I wouldn't think too hard about it. Just know that if it says calculate the mass of 1 mole sodium atoms, you times 1 times the molar mass on the periodic table. I'm going to put out about 8 videos. So, I mean, if you've got the slides there, you can quite easily calculate this, but I'm going to leave it for 2 minutes. And I want you to think how you would calculate this. You can cheat and skip ahead, that's fine. But sit there, and how would I calculate the mass of 3 moles of O2 molecules? I need 2 minutes. And then I will do it on the screen in the whiteboard. So, just a few things to think of. A bit tricky with O2. Another 30, 45 seconds. 30 seconds until it's 5:40 p.m. And I will. So I'll teach you a simple one. So the mass of 3 moles of O2 molecules. So oxygen is 16.00. So 2 times 16.00 equals the molar mass of O2. So to calculate the molar mass of something, we times, this is of a compound like oxygen, where there's 2 atoms, 2 or more atoms. So we have 2 times the molar mass of oxygen as it exists by itself, equals 32. So molar, so the mass of times 32, which would also equal 96. So we find the molar mass of oxygen, which would be 16.00. We times that by 2 because it's O2, which gives us the molar mass of, well, the mass of 1 mole of O2. It says there's 3, so we times 32 times 3, and we get 96. So, again, I will let you think. So we are going from here, we're going from moles to grams. Moles to grams, very important. Here, we're going from grams or kilograms to moles. I'm going to give another 2 minutes to sit and have a think about how we could calculate this. I mean, you could jump in again if you want, but have a think about how we would do it. One more minute. So, things we need to remember. We have 1 kilogram. So if we look at the molar masses in the periodic table, they are in grams per mole. They're not in kilograms per mole. So we have to convert 1 kilogram, 1,000 grams. So the easy way, the moles equals mass divided by the molar mass. So we have 1,000 grams is our mass. So carbon is 12 grams per mole plus 16, which is oxygen, times 2. gives CO2 a molar mass of 4 grams per mole. So we take 1,000 grams, which is our mass, and then we divide it by the molar mass, which is 44 grams per mole. So when we're dividing, we're getting rid of the grams, and we are left with 22.7 grams per mole. So again, I'll do a video on that. I imagine I'll probably do a lot of videos this week. It gets a little bit more complex than we've been doing previously from this week. So Avogadro's constant and calculations using it to find how many atoms of something is. So helium, so how many atoms are in 0.200 moles of helium gas? So we would do 0.200 times we would simply take the number of moles and the atoms. We take the moles, so this is 0.200 moles times Avogadro's constant. Gives us, I'm not going to use my calculator, 1.21 10 to the power of 23 atoms. So we're taking the number of moles times by 1 mole, or the Avogadro's number, which is 1 mole, gives us 1.21 times 10 to the power of 23 helium atoms. So, do this one as well. So carbon dioxide exists as molecules of CO2. How many molecules are there in 125 mole of carbon dioxide? So we have 0.125 moles of CO2. We know Avogadro's constant. So we simply times the number of moles by Avogadro's constant. So it equals 7.53 times 10 to the power of 23 molecules. So we'll do one more. So how many molecules of 19.70 grams of gold? How many atoms? How, again, don't answer, but how might we figure this out? What do we need to know? We need to know the molar mass. Gold. Go to the periodic table, find AU and find out its mass. So we will find that there are molar mass is 197 grams per mole. So we would then divide 19.7 grams by the molar mass, which gives us 10 moles. So all this is doing is all we're being given is the mass of gold. And again, this makes up stoichiometry, which we'll do next, I think. So we go from the mass of gold to the number of moles. So we do that by dividing the mass in grams by the molar mass, which gives us 0.10 moles of gold. We know Avogadro's number. So we would divide 10 times 6.022 times 10 to the power of 23, which would give us 0.6. I mean, yeah, if you want to put that into your calculator and figure out, I'm not going to. The answer is largely irrelevant. It's the equation that you want. So, if they ask how many atoms of something in amount of grams of a substance, we need to find the molar mass of gold. So we divide it, the mass, by the molar mass, that's 10. And then we times that by Avogadro's constant, which gives us the number of atoms. Right, I'm going to do lots of videos for this week because it's quite an in-depth topic. So keep a lookout for those, and I will see you next week.